Great. So welcome everyone to this another tunneling in QFT series. We're hoping to fill up the 2026 slots. We have coming up next month Javier Subils from Utrecht talking about a microscopic description of critical bubbles, so more bubble stuff. And then that's in February, and then in March we have Gianluca Lagnese talking about, I think, quantum kind of the experimental side of looking at tunneling and that kind of force vacuum decay. But today we have Jorinde talking to us about bubble wall velocities, wall velocities and friction in cosmological phase transitions. So Jorinde is currently a CERN research fellow at the theory group in CERN, and yeah, really a world expert on this topic. So very happy to hear from you. Please take it away, Jorinde.
Thanks a lot, Ollie. Well, very nice to be here and to talk to you about this work. Okay, the seminar is called Tunneling in QFT. I'm talking a bit more about what happens after the tunneling, but I hope you find that interesting as well. I'm talking about work based on, the presentation is based on these 3 papers with some amazing collaborators, Andreas Ekstad, Ollie Gold, Jonas Hirvonen, Benoit Laurent, Lauri Nimi, Philip Schicho, and Thomas Constantin. And a lot of them are in the audience, so if I don't know any answer, then ask them. Okay, so let's start with a bit of an introduction. Well, we are all here because we think that the universe might have experienced one or multiple first-order phase transitions, or at least that we find this an interesting possibility. That is interesting because there are scenarios that predict, for example, the generation of the baryon asymmetry or dark matter in a phase transition. This phase transition could also source a gravitational wave signal when the bubbles collide. That's kind of what this cartoon is showing, collision of bubbles, and they can source gravitational waves, which might be observable with the next generation of gravitational wave experiments, such as the Einstein telescope or LISA, or even with ongoing pulsar timing arrays, which are already seeing stochastic gravitational wave signal, although I think it is more likely that that comes from supermassive black holes, but who knows?
Oh, is there a problem with
Jorinde,
audio?
we've lost your sound.
Yeah, there's an issue with audio. We can't hear you.
I think.
Yep.
Yes, we can hear you now.
Okay. I don't know what's up with these headphones. So should I go back how much?
Oh,
No, we only lost a few seconds.
Yep.
Okay, good. So I was saying this is exciting. It would be consequence of physics beyond the standard model, something new coupling to the Higgs, maybe a dark sector. And what I want to discuss in this talk is with what velocity do these bubbles expand? That's the first part of the talk. And then the second is how do we describe the interactions between the plasma and the scalar if we are forced to, or if we have to zoom out to a larger length scale. So I will make this a bit more concrete in the end. So why do we want to know what is the wall velocity? Well, because the phenomenology of some of the processes I showed in the previous slide depend on the wall velocity. For example, if you look at models that generate the matter-antimatter asymmetry in the electric phase transition, and you compute the baryon asymmetry as a function of the wall velocity, you see that there's a dependence. So these graphs were from Benoit and Jim Klein. It's for 2 different models of electric baryogenesis in 2 different mechanisms. The red one is the more reliable one. You see particularly in this right graph that there is a relatively strong dependence on the wall velocity, and if you wouldn't know what that parameter is, then well, you have a large uncertainty in your baryon asymmetry. There are dark matter generation mechanisms in phase transitions. For example, filtered dark matter, where you have some heavy dark matter candidate that gets kind of squeezed between the bubbles that are very slow, so these particles cannot enter. There are dark matter generation mechanisms where you actually produce very heavy dark matter by interactions with a very fast wall. So this is kind of the opposite regime where the wall has to be very fast. But okay, in both cases, the wall velocity determines whether you can or cannot produce the dark matter abundance. And then lastly, the gravitational wave spectrum depends on the wall velocity. As we see here, this is a graph predicted with the sound shell model. Everything else is kept fixed, but the wall velocity is varied, and you see that the spectrum changes amplitude and shape. So, okay, I think that is all important motivation to try to figure out what the wall velocity is. So let's look at the computation. I forgot to say in the beginning, if you have questions during the talk, then please feel free to interrupt me. So we consider a weakly coupled system. So in this talk, I'm not talking about strong interactions. We have a bubble wall that is sketched here, and we have particles in the plasma. Of course, this is a cartoon. This is not to scale. These particles are, of course, well, not so big. Now, when the phase transition happens, there's a vacuum release, and this provides a push outward. So the bubble wants to accelerate and grow. But there are also forces that are decelerating the wall, and these are the friction from the plasma particles that can either reflect on the wall or they can maybe enter, but when they enter, they become more massive, and this provides a force that opposes the acceleration. And on top of that, there can be hydrodynamic back reaction effects, and these occur because a faster wall heats up the plasma more, and when the temperature increases, the vacuum energy difference becomes smaller, and that makes the expansion less favorable. So what we do is we look for a wall velocity where the pressure pushing outward and inward is equal. And then, well, there's no net pressure, so the wall stops to accelerate, and that we define as the bubble wall velocity, and that we try to compute. Now let's put this into equations. First, the scalar field. So we can have one or multiple scalar fields. If you have a two-step phase transition, for example, then there's two fields that are relevant. So they have an index I here. And their equation is like a modified Klein-Gordon equation, where we now also have this dissipative term, where this delta F is the deviation from equilibrium. So F is the distribution of plasma particles. There's an equilibrium part that has been absorbed in this effective potential, and there's an out of equilibrium part that contributes to the friction. And as you see, the particles that are most massive, like the top quark or the W, give the largest contribution to the friction. Let's assume for a moment that we know what this delta F is. Then still, to solve this equation, we have to know what the fluid velocity and the temperature profile are, because they enter here, or just the temperature actually. And this gets solved from energy momentum conservation. Now, if we assume that the wall moves in the z direction, then energy momentum conservation gives us these two equations for the fluid velocity profile. The temperature enters here in this W, which is the enthalpy. And these are out of equilibrium contributions. The right-hand side, these are constants, so we can determine them far away from the wall, and there we can just use ordinary hydrodynamics. So we can forget about the wall, just solve the right-hand side with hydrodynamics, and then we can solve this equation. But we still need to know what delta F is and these T outs here. And this follows from the Boltzmann equation for the plasma particles. On the left-hand side, we have a flow term. It contains a derivative of the mass here. So this is the term that sources deviation from equilibrium. And on the right-hand side, we have the collision term, which parameterizes or which describes the interactions between the particles. Now, this is what makes this equation very hard to solve, because these collision terms contain integrals over the momenta of the interacting particles, and they contain terms that are polynomials in f, the function we try to solve for, up to order 4. So this equation is very nonlinear, but in practice we often linearize it, the right-hand side. Well, the left-hand side is already linear. And this is really the state of the art for wall velocity computations. I'll come back to how good of an approximation that is. So we have written a code. It's called WallGo, and it tells you how fast does the wall go. It's the first publicly available code for the computation of the wall velocity, including out of equilibrium contributions. I'll show a little bit quickly what it does, because I would like to go to the results. But of course, if you want to know more details, then you can interrupt me and ask, or ask at the end. So imagine that you're interested in computing the wall velocity for some model. Then you can determine which particles in that model you want to treat as out of equilibrium and which interactions you want to include. Then WallGo can compute for you the 2-to-2 matrix elements in a module that is called WallGo matrix, and this is based on DrellGo. Then for these matrix elements, WallGo collision computes the corresponding collision terms in C++, and then this is all fed into actual WallGo, which solves the equation of motion for the scalar field. It solves also the fluid equations for the velocity and temperature profile, and the Boltzmann equations for the out of equilibrium particles that you specify. So, as I've just said, the model and the set of out of equilibrium particles are completely user-defined. To be a bit more concrete, here I'm showing again the scalar field equation of motion. We do not solve this exactly. We assume a tangent profile for every field participating in the phase transition, and then we solve for the wall velocity and the widths and offsets of these fields by minimizing the action. We solve iteratively, so first we solve for the profiles of the field, the temperature and the velocity. We plug that into the Boltzmann equation to solve for delta F, and then we iterate until we find the wall velocity for which the total pressure vanishes. Let's look again at the Boltzmann equation. As I said, we linearize it, and then we use the spectral method that Benoit developed together with Jim Klein. And that is an expansion of the delta F, so the deviation from equilibrium, in a basis of Chebyshev polynomials, as shown here. So we use 3 polynomials, one for the distance from the wall, and 2 for the momenta. And when you do this and you introduce a grid, then the Boltzmann equation becomes a matrix equation, and the collision terms have to be computed for every basis element. So this we do before the entire computation, because it's computationally expensive, and then we in the actual computation in WallGo, we have to solve this matrix equation. Okay, here are some examples of a result. So we take here the XSM, so the standard model coupled to a singlet, the second step of a two-step phase transition. This is here the singlet self-coupling is fixed, and then we make a scan through the parameter space, and you see how the wall velocity, shown in color, depends on the parameters. Here the red band shows that no solution was found, so the wall might actually accelerate to much larger values, but okay, WallGo doesn't work in that regime, so we don't exactly know what happens here. So these are the deflagration or hybrid solutions, and here on the right we compute the detonation solutions. So those are the faster ones, and you see that there's a bigger part of parameter space that has a solution in the deflagration or hybrid regime than in the detonation regime. The nice thing about the spectral method is that we can choose the number of polynomials that we take. Of course, this comes with a numerical cost, so you want to optimize where you have good convergence but not an enormous amount of computation time. And this is a test, again, for the XSM. keeping the number of basis polynomials in the spatial direction in the momentum direction fixed and varying in the spatial direction. And here it's the other way around. So we keep them fixed in the spatial direction and vary in the momentum direction. And you see that indeed, if you pick them large enough, the solution converges very nicely to a fixed value of the wall velocity. And in what I'm going to show in the rest of this talk, I think we've always used n equals 11 for the number of spatial polynomials, momentum polynomials. And in the spatial direction, we use more because those are less computationally expensive. Okay, so when we wrote WOGO, our goal was twofold. One was, to provide a tool and to improve computations of gravitational waves, baryon asymmetry, etc., because in most computations, people simply guessed the wall velocity. But our other goal was to understand what is the theoretical error in the wall velocity, and of course, we want to reduce it. So now I'm going to show the results of a recent paper where we used WOGO to get an estimate of the theoretical error in the wall velocity, and then reducing that error will be the topic of future work. We did a test in two benchmark models. The first I've already shown some results of, the XSM. So we used a variant of this model with Z2 symmetry. So we take the standard model, we just couple it to one gauge singlet, a real gauge singlet. And we focus on the parameter space where the phase transition is two-step. So in the first step, the singlet gets only a VEV, and then the second step, that singlet goes back to zero, and the Higgs gets its VEV, and we focus only on the second step of the phase transition. The other benchmark model is the inert doublet model, and that is a special case of the 2 Higgs doublet model, where now this new doublet has no VEV at zero temperature. In this case, the phase transition gets radiatively generated. So only through loop corrections from this new field to the effective potential. And the Higgs gets only a VEV. So this new doublet always remains at zero VEV. The model has 4 new bosons. They're typically called A, H, and H8 plus minus. And in our implementation, or in our benchmark model, we take H to be light, and the other 3 we take to be heavy, but also of the same mass. And that mass is of the order of the electroweak phase transition scale. So they're relatively heavy and they can just provide some friction. Okay, so now let's look into some sources of uncertainty. The first is, which set of out of equilibrium particles do you consider in your computation, and which interactions do you allow between them? So in principle, all particles that have a mass get pushed out of equilibrium by the passing bubble, and also by the variations in the temperature and the fluid profile. So in principle, in a full computation, you would actually have to allow all particles to be out of equilibrium. However, that is numerically very expensive to solve the Boltzmann equation, but also to compute the collision terms for all of these particles. So in practice, one tracks only the heaviest particles and then also maybe the particles with the largest number of degrees of freedom. And in the collision terms, we focus only on the strongest interaction to also keep that manageable. Now, of course, there's a trade-off between numerical cost and accuracy. Including more might gain you some accuracy, but it will also take longer. So this graph here illustrates this trade-off. This is a slice through the parameter space of the XSM. The mass is kept fixed here and the Porto coupling is varied. And the green line shows the result of the wall velocity if you allow only the top out of equilibrium and you allow that to interact only via QCD. Now the pink line here shows what happens if you also allow the gluon out of equilibrium. You see that the effect is mild, especially here at larger wall velocities, and that is also to be expected because the gluon itself does not give friction on the Higgs wall. So the effect of taking the gluon out of equilibrium is only indirect via its interactions with the top quark. The blue line considers what happens if you do not only allow strong interactions, QCD interactions, but also weak interactions. These interactions are, of course, well, weaker than the strong interactions, but you see a significant result here. So the wall velocity goes up from this green line to the blue line. The reason is that now the top quarks that have to be split into left-handed and right-handed quarks have more opportunity to relax towards equilibrium because the collision terms are stronger. And as a result, the wall velocity is larger because the friction was reduced. Okay, now, if we're including weak interactions, maybe we should also include the W out of equilibrium. That's this yellow line. So the W has also 6 degrees of freedom because we're actually treating the W as the same as the Z. So we're completely neglecting U1 interactions. And it's also relatively heavy. And indeed, you see that the wall velocity now goes down from this additional source of friction. Actually, we end up almost exactly where we started when we took only the top and QCD into consideration, but that must be a coincidence. So I don't think this holds in general. And then the last test that we did was to put the W back into equilibrium, but take the bottom out of equilibrium. Now the bottom has a mass, but it's much smaller than the top. And indeed, we see only a relatively small correction to the wall velocity. So this graph really shows that, you have to make a choice about which particles to take out of equilibrium and which not. But that in general, although this graph might suggest it, but just the top and QCD will probably not give you the full picture. Okay, now let's discuss the effective potential. The effective potential enters in the equation of motion of the scalar field. We use it to describe the phase transition, and typically you arrive at the effective potential that you need by starting with zero temperature, tree-level potential, and then you add loop corrections to it, and these loop corrections are temperature dependent, and then you get a temperature dependent effective potential. Now, what is known from studies of gravitational wave spectra or from simply thermodynamics, studies of thermodynamics quantities, is that a one-loop computation of the thermal parameters is often not sufficient to get a good accuracy. That's demonstrated here in this graph that shows a gravitational wave spectrum. The light region shows what you get with one loop. The darker blue region when you include beyond one loop effects, and you see that it really shrinks the uncertainty. So it's quite essential to include these beyond one loop effects. However, in every computation of the bubble wall velocity, the effective potential in the scalar field equations of motion is just the one loop effective potential. Okay, you might think, what's the problem? I can just put the two-loop effective potential in there, but this would also be completely ad hoc. No one has really derived what would be the quantity that has to enter there. So this is not what we want to do, just put the two-loop effective potential there. But what we want to do is to try and quantify the dependence on, in uncertainties in the thermodynamics on the wall velocity. We do that in two ways. What we first do in the XSM is vary the value of the nucleation temperature. Because associated to these uncertainties in the effective potential, there's also an uncertainty in how to compute the nucleation temperature. And here we quantify how big the effect on the wall velocity is. So the blue line shows for this model what we computed to be the nucleation temperature, and then the colored lines show what happens if you make the nucleation temperature larger, so the phase transition less strong in pink, or if you make the nucleation temperature lower, so the phase transition becomes stronger, then you see that the wall velocity goes up. As you can see, there's quite a spread. So if indeed the uncertainty in the nucleation temperature would be of this order, then you really get the order 1 corrections to the wall velocity. Another way to quantify the uncertainty from thermodynamics is to look directly at the effective potential. And this we did for the IDM, the inner doublet model. So the dark colors here show a result using the potential with daisy resummation. This pink shows local thermal equilibrium, blue shows the top out of equilibrium, and yellow the top and the W. And then the light colored ones show what you get when you neglect the daisy resummation term. Now, this is, of course, even a less accurate approximation of the effective potential, but it gives us a measure of how big the effects of different orders in the computation are. And we see that the effect is significant. So we get order 30% corrections to the wall velocity between the potential with and without daisy resummation. So I think this is a good motivation to really look into, what is the appropriate effective potential or quantity to put in the scalar equation of motion. Okay, another source of uncertainty can come from the collision terms that appear on the right-hand side of the Boltzmann equation. I'm showing here the linearized collision term. So it is an integral over the momenta of the other three particles, so not the particle in the Boltzmann equation, but the one it interacts with. This delta function here enforces energy momentum conservation. This is the matrix elements for 2-to-2 scattering, which is the only type that we currently include. And then these here are population factors. So F are the distribution functions, and this big F also is a function of the distribution function and the deviation from equilibrium. So what we take into account here are 2-to-2 diagrams, as I said. And now let's consider, for example, a top quark scattering with another quark. Then the matrix element could have contributions like this, where S, U, and T are the Mandelstam variables, of course up to numerical prefactors and coupling constants. Now, when the momentum transfer is small, the Mandelstam variables T and U can go to 0, and that may give you a divergence here. That's of course not good because that's not a physical answer. And what is then usually done in these computations is to regulate this divergence by using the hard thermal loop self-energy in the propagator. So this regulates the divergence, nothing goes to 0 anymore, so you get a physical result. What is often employed in these computations, or actually always in wall velocity computations, is the so-called leading log approximation. This implies that you only keep the U and the T channels, and as I just said, you regularize the propagator with the hard thermal loop self-energy. So let's have a closer look at these divergences. So I've now, so naively, you would think that terms that scale as 1/t are indeed logarithmically divergent, hence the name leading log. But there are also terms that scale as 1/t², which would be power law divergent. Let's look into a bit more detail. So we can rewrite the collision term a little bit. So I've just rewritten this population factor, where now chi parameterizes the deviation from equilibrium with some rescaling here. Okay, so if particle A and C appearing here and here are identical, as well as B and D, and now we go to the limit where P3 minus P1 is small, which corresponds to T going to 0, so this is where you would have the divergence, then we can Taylor expand this term, and because these chi's for A and C are the same, we get an explicit factor of the momentum here in front. Now this softens the divergence from a power law to log divergent and from logarithmic to finite, because this is proportional to T. Now, of course, this only works for identical particles because I relied on the fact that this chi and this chi are the same function. For non-identical particles, the power law can in fact still persist. Okay, so let's look at the weak interaction, because in QCD you actually only get logarithmic divergences, but for the weak interaction it looks like you might actually get power divergences. And in that case, we expect the collision term to scale as g squared when it is power law divergent, and as g fourth over log inverse g for the logarithmically divergent one. So we tested this. Here I'm showing a matrix elements of top-bottom scattering. The first term here is an S channel, so it is beyond leading log. We don't consider it. Then we have the term here with the T channel where these particles are identical. Therefore, this divergence is expected to be logarithmic. And here on the right, we have a U channel with a T and a B that are non-identical. And therefore, we expect this to be power law divergent, or power law enhanced, of course, because we've regulated the divergence. We tested this by computing or reconstructing the collision term in Woolgo for different values of the coupling. And that is shown here in this graph. So we're varying the weak coupling constant. We've only considered a collision term from this particular diagram. And indeed, we see a scaling. This is a fit to 1 over g squared. And you see that indeed the collision term follows this behavior. So if we have the weak interaction, then we get power law enhanced terms. And here on the right, we focus on these type of diagrams. We discard this one, and indeed we see that the collision term behaves like a logarithm. Now, this is actually interesting if we now look back at this graph that I showed already before, because in many computations, the weak interactions are discarded because, well, they are weaker and they're suppressed by their coupling, which is much smaller than the one of the strong interaction. But as I've just argued, there are certain diagrams that are power law enhanced and therefore can give a significant contribution. And I think that is the reason that if you look at the difference between this green and blue line, it is actually quite significant. And part of the reason might be these power enhanced collision terms. Okay, now leading log is of course not even leading order. It's not expected to be a fantastic approximation. But what would we have to do to go beyond leading log? If we would want to compute the full leading order result, we have to do a number of things. We have to include again the S channel diagram and also the subleading T and U channel diagrams. 2-to-2 scattering is not enough. We also have to include 1-to-2 diagrams. And these 1-to-2 diagrams come with soft emissions that have to be resummed. This is called LPM resummation. And furthermore, we would have to include the momentum dependence in the hard thermal loop self-energy. Now, this is really non-trivial. It has been done, but for transport coefficients by Arnold Moriyafi, and they found about corrections to the transport coefficients of the order of 25% at next to leading log. For the wall velocity, this computation has not been done. We have also not done that yet. But what we try now is to estimate how big the uncertainty on the wall velocity is associated to the uncertainty in the collision terms. We do that in the following way. Woolgo has an option to multiply all collision terms with some number that is not equal to 1, and that number is called the collision multiplier. So what we do is we vary this collision multiplier to mimic the uncertainty in the collision term associated to the uncertainty in the leading log approximation. I show this here for the XSM. So on the x-axis, you see the collision multiplier, on the y-axis, the wall velocity, and in different colors, different benchmark points. So in the middle, we have the value for the standard model leading log collision term. And then here in the gray band, we show what we feel is more or less the range of uncertainty in the collision terms, and then you see how much the wall velocity varies. And you see that the variation is actually quite significant, more for smaller wall velocities, but it indicates that this leading log approximation might actually have a significant effect on the wall velocity. This was the XSM. This is the IDM with different particles out of equilibrium, just the top and the W, the top, the W, and the new heavy scalar. But the picture is the same, quite significant changes in the wall velocity. Then the last source of uncertainty is that I want to discuss now is the linearization of the Boltzmann equation. What I show here is an estimate of the contribution to the pressure by what would be the next to leading order term in linearization. Now, WOGO does not compute anything beyond the linear order, but we make an estimate, and that is what's shown in this graph. So it shows the ratio of the pressures corresponding to this term divided by the pressure that is actually measured with WOGO. And you see that throughout the entire parameter scan, this number is relatively small, indicating that linearization is not something we have to worry about so much. Okay, so let me summarize the results of our study of the uncertainties. So these are, for the two benchmark models, the different sources of uncertainty and our estimate for their size. And as you can see, they're actually quite large sources of uncertainty. For example, the leading log approximation, but also in the effective potential. So this is maybe not the most optimistic message, but on the other hand, there's a lot of interesting work to be done in the coming year. So coming years. So I hope that in some time from now we can show this table again and with smaller errors. Okay, I would go now to the last part of the talk, but maybe I check if there are any questions. No? Okay, then I just move on. Okay, so now I want to talk about the scalar damping term. Let me explain a bit what I mean with that. Sometimes it is not feasible to solve the Boltzmann equations for the out of equilibrium particles. And of course, this could be because you don't have a computer, but I don't mean that situation. I mean, so let's say you're solving lattice simulations for gravitational wave formation, then you have to simulate many bubbles. So you have to resolve the length scales of the bubbles, but you also have to resolve the length scale of the bubble wall. Now, this is very challenging, and it is not feasible to also resolve the length scale on which the Boltzmann equation is relevant. So in these simulations, what is typically done is one makes use of a sort of phenomenological friction term that is added to the right-hand side of the energy momentum conservation equation. It's parameterized here in terms of this theta, and the scalar field equation of motion looks like this. So this here I call the scalar damping term. In many simulations, this theta is chosen to be a constant, but in some simulations, it's chosen to have this form, where this eta tilde is now a constant. So what I want to discuss now is when this form of the friction is consistent with the Boltzmann equation, and also how can we derive its value, for example, with WOGO. Okay, so let's first discuss the shape of this term. I'm showing again a Boltzmann equation here, but now I think it's most easy to illustrate this using the fluid ansatz. So now the Boltzmann equation looks a bit differently from what I've been showing before. Sorry for that. So this is a system with a top and a W out of equilibrium. The Boltzmann equation consists of a flow term here that is the terms with the A. Then we have a collision term. And we have a source term. And the source term is a function of the mass derivative. The Q's are parameterize the deviations from equilibrium. So if you would take a basis with 3 deviations of equilibrium, it's the chemical potential, the deviation in the temperature, and the deviation in the fluid velocity. You can also work with an extended fluid ansatz, then there are more here, but that's not really the point here. Okay, now the scalar field equation of motion looks like before. We now write the friction as omega delta. And omega delta can be derived from the solution to the Boltzmann equation in this way. So this V here just contains some numerical factors. We have again the proportionality to the derivative of the mass term like before, and nx is just the number of degrees of freedom. So, okay, we have to solve this Q from the Boltzmann equation like before, and plug it in here to get the friction. Okay.
Can I
Yeah.
ask questions? What is QL in the carbon equation of motions? QL, the
Yeah.
subscript.
This is light degrees of freedom.
Okay, thanks.
Yeah. Sorry. Thanks for asking. So these are assumed to not be pushed out of equilibrium. Therefore, they have no source. Okay. So now we take the local limit of the Boltzmann equation, and that is the limit of very large collisions, so large that the flow term can be neglected. So if we look again here, we throw away this term and we keep only these two, such that the solution is quite simple. It's just the inverse of the collision term times the source. Okay, so now we have a solution for the deviations of equilibrium. This is, by the way, analogous to Chapman-Enskog approximation. And we plug this now into this expression here, also putting in the explicit expression for the source, which is a derivative of the mass with respect to z. And then we get the following approximation here. Now, in most theories, the derivative of the mass squared with phi gives you a phi. So that's this term here. This is here. So this term here gives you eta. Okay, so this is actually the term that we already saw earlier. I can show it again. It's this. So it has exactly this form as long as theta is chosen to be this. Okay, so that is nice. There's a physical motivation for such a term, as long as we're in the local limit, which I will discuss a bit more. First, let's see if we can compute this thing with Wolgo. And we can. We use again the collision multiplier. And the reason we do that is we have to enforce that we're in the local limit. So using the collision multiplier, we set it to 100 in this graph. We make sure that the collisions are really dominant. We're actually quite close then to local thermal equilibrium, but not exactly. And then we can compute what is the value of the friction term. Okay, we have to rescale it then again because we have rescaled the collision term. We get the following values. So, okay, these numbers maybe don't mean that much, but what you can see clearly is that the left-handed top quark gives a significantly smaller friction than the right-handed one, and the reason is that the left-handed one also feels these weak interactions. What you can see very nicely in this graph, so these are the friction terms actually computed from Wolgo, so from a real Boltzmann equation, all rescaled so that they all fall on top of each other. So this is for the tops and for the W, but also the friction term that is used in this scalar damping approximation. And you see that they all coincide very, very nicely. So this shows that indeed, if you're in the appropriate limit, this friction term seems to be a good approximation for the actual friction that you would get out of the Boltzmann equation. So that is good news because that gives validation to how it is done in simulations. But let's discuss for a moment whether this local limit is really valid, because in the previous graph, I enforced it by hand. So let's now decrease the collision multiplier. And we see indeed that if we make it smaller, so we make the collision term smaller, and therefore the flow term becomes more relevant. And so the solid lines here show the result of Wogo, and the dashed line shows the local approximation to the friction term. And you see that this is in the standard model with the light Higgs, if we keep the collision multiplier equal to 1, the local approximation is quite reasonable. But if we make Q smaller than 1, so the collision terms become small, then you see that indeed this local limit doesn't work very well. And another way to investigate this scaling is by looking at the integrated friction. So here I integrated the friction over the entire wall. And again, I varied Q, so the collision multiplier. And we see that here on the right, where we have large collision multipliers, indeed, this scales in the way that we would expect to be in the local limit. So the dashed line shows the scaling that is appropriate for the local limit, and we see that we are indeed in that scaling. But then if we make the collision term smaller, we see deviations between that expected scaling and the actual scaling observed in Wogo. So for the W, we see that here, when Q is actually 1, the deviation between the local limit and the assumption of local limit versus the actual scaling is a factor 2. That is what these vertical lines indicate. For the top quarks, this happens actually at larger values of Q, implying that for the tops, the local limit is still relatively safe or relatively appropriate in the standard model, whereas for the W, it is already a bit borderline. So the friction of the standard model W is not really accurately described with such a local term. Then lastly, I would like to point out that the W is problematic in more than one way. And the reason is that there seems to be an IR divergence in its value. This table here shows computation of the friction coefficient of the W in the fluid ansatz approach for different values of the basis size. This here is the friction, the scalar damping I've been discussing so far. These are next to leading order corrections. But the main point here is that you see that convergence is not very good. So you increase the number of basis elements, and it has quite a strong effect. It doesn't look like it has converged. In Wogo, we see a somewhat similar picture. Let's first look at this pink line, which puts only the vacuum mass in the Boltzmann equation. So only the VAV-dependent mass, that is the same approximation as was made here. And you see that the friction coefficient depends, quite strongly on the number of basis polynomials. If you increase the number of basis polynomials, you also get more sensitive to the IR. So if there is an IR divergence, then this is indeed the expected behavior. Not very good. If, however, we put the asymptotic mass in the Boltzmann equation, we get this blue dashed line. So now there is a temperature-dependent mass in the Boltzmann equation that does not depend on the field. So also in the symmetric phase, there is a non-zero mass. And we see that this makes the dependence on the momentum grid size at least milder. So that also enforces this idea that this is an IR effect, which gets somehow regulated here. But I think this requires a bit more consideration, because I think that these numbers have to be taken with a grain of salt. Okay, that brings me to summary. The wall velocity is important if you want to compute particle production or gravitational wave production in first-order phase transitions. We've written Wogo. That is the first publicly available code for the computation of the wall velocity, including out-of-equilibrium effects. We've used it now to study theoretical uncertainties in the wall velocity computation. We found actually many sources of uncertainties, so there is work to be done, and hopefully we can improve this in the future. Now, in, for example, gravitational wave simulations, you cannot solve Boltzmann equations, but you need a description for the friction as a coupling between the fluid and the scalar field. That is done via scalar damping. We've investigated the validity of the usually you assumed local limit. We've shown that that is reasonably satisfied for the W in the top of the standard model, and we determined the friction coefficients of these terms. All right, thank you.
Thank you.
Thanks a lot, Jorinde. Very nice talk. Yeah, let's open it up now for questions, please. Tom, please go ahead.
Hami?
Hi, Jorinde.
Hi.
So could you maybe say that this Paul convergence for the W bosons is maybe evidence that we need to go beyond like a Boltzmann description for it due to certain infrared enhancements, or is it something else?
Yes, I think so, yes. There are some works by Dietrich Bödecker and Guy Moore who also make this claim, and they use a different treatment for these bosons. They use some overdamped evolution equation. So yes, I think you're right, but I think doing this systematically is another question. Yeah.
Okay. And I'll ask another question later if there's time. Thank you.
Carlo, then?
Right. I also have two questions. Let me first ask the first one then. Okay, first, wonderful talk. Thanks a lot and impressive work. So on slide 31, you showed the dependence of the bubble wall velocity on the precise value of the nucleation temperature. Oh, what happened?
Yeah, good question. I think 31, right?
I think it was 31, yes.
Sorry, I get a weird notification now every time I try to share.
Okay, maybe the slide is also not so important for it.
I'm just not gonna go to full screen then. This one?
Yes, precisely. So if I understood it correctly, also in like the summary table, eventually you show that the nucleation temperature, or the precise value of it, it's super important for the computation of the bubble wall velocity, like a 100% shift in the bubble wall velocity is possible. Now, I was asking myself in another project if actually why we take the nucleation temperature here if we eventually want to evaluate all quantities at the percolation temperature. So there are these Higgs assimilations by Thomas and by Isaac, and they find that there's actually this time evolution of the kinetic energy fraction, right? And eventually they compute this integrated quantity, which is basically averaged over the time evolution. Would it make sense here also to compute the equilibrium bubble wall velocity at different temperatures and then take an average?
Okay, let me first address the first point. I think you are right in that the percolation temperature is in a way more appropriate. In a way, I'm being a bit sloppy here in assuming that the nucleation temperature and the percolation temperature are relatively close to each other. So, and for these not too strong phase transitions, I think this is not too bad of an approximation, but okay, if you're trying to be precise, we should be precise. So that I think you're right. About your other question, I'm not sure if I completely understood because, so first of all, you could do it. You can easily compute the wall velocity for all temperatures, but I'm not sure if that helps because you have, at this later stage of the computation, you don't have bubbles in isolation anymore, right? So I don't know if that is still very meaningful, if that is still a meaningful quantity.
Me neither. I don't know,
but maybe it's something But what made you think it? Because in their computation, the wall velocity is fixed, right? So
Yeah. In their computation, the bubble wall velocity is fixed, but given that apparently, depending on when precisely that you compute the bubble velocity and the first order phase transition can take place over a long period in time or in temperature, maybe it makes more sense to just consider the bubble wall velocity not an equation, but at another point in time, or taking like an integrated quantity that sums up all these effects.
yeah, okay. Yes, I would imagine that might gain you some accuracy. I would think it's maybe hard to do it in practice in a sort of controlled way, but yeah, I think that is reasonable. Yeah.
Okay. Tom, maybe do you want to continue with your second question before I ask my
I
second
mean,
one?
unless there's anyone else.
Just you two at the moment, so go for it, Tom.
Okay. So with the collision multiplier, um, so my understanding is that you're taking it as a sort of, I don't know, as like the effective NLL effects is sort of representing it. Yeah. So it's obviously if it's just a constant multiplier, you're missing the momentum structure. Do you expect this to be fairly robust, or is there anything you might miss?
I don't think that this is I don't think this is very robust because also what we do is we multiply everything with the same number. Whereas it looks like we have power law enhanced terms, we have leading logarithmic terms. I think they are affected differently by this finite order in perturbation theory. So I don't think any of us had the idea that this is a very robust way of estimating the error. I do think it does give you an idea of, okay, if leading log could give you order one corrections to the collision term, let's see what correction to the wall velocity you get when there are order one errors in your collisions. So, but it's not much more than that, I would say. And yeah, you're absolutely right.
Okay, thank you.
So
Go for it, Colin.
if I can ask another one. So super naive question, phenol question. Why is 2-to-2 scattering the most important kind of scattering?
Okay, I think it is because 2-to-2 has this logarithmic divergence slash enhancement and 1-to-2 does not, but maybe someone can confirm this. Okay, no one objects, so I think that is
I guess if you have web dependence, some of the other things become more important. But I think in most cases we kind of fixed it and checked just for this scenario what is the actual dependence of the web. But I guess 1-to-3 or like some odd value, 1-to-3 scattering could become more important as soon as you have web dependent couplings, and I think then it can also be very relevant.
Okay, thank you. Thanks.
Thanks.
Can I ask a very naive question?
Go for it.
So at some point you actually consider gluons to be out of equilibrium. Is that realistic or just consider it for fun now?
Well, I think it's realistic in the sense that well, the code decides for us whether it is realistic, right? And it showed
Yeah.
that well, okay, that here in this regime you barely see it, right? It's somewhere below the other line. So I think here it just shows it really doesn't matter. The gluon just follows the equilibrium distribution function, so you don't have to bother. Here the difference is a bit larger. So apparently the gluon gets pushed out of equilibrium a little bit.
Yeah, wait, so can I see whether gluons are out of equilibrium or not from this plot? Or, I mean,
Yeah, you can because so if you what you have to compare here is the green line Maybe I can just zoom in. So this green line, which has only strong interactions and a top out of equilibrium, with this
Yes.
pink dotted line, where we say, okay, we allow the top as well as the glue out of equilibrium. Everything else we keep the same. And you see that apparently allowing the gluon to be out of equilibrium does suppress the wall velocity a little bit. So it suggests that this assumption here that the gluon is completely in equilibrium, made on the green line, okay, is not 100% correct. I think that's what you can conclude from it. But it is not, especially here, it is not the strongest effect that you see.
Okay. Okay, I thought you just put your gluons out of equilibrium by hand. Oh, okay, I see. So you actually solve your Boltzmann equation. So essentially,
Yeah.
okay, I see. So
Right.
no,
I would rather say that with the green line, we put them in equilibrium by hand because we don't test it. We just don't solve their Boltzmann equation and we assume that the species are there, but they follow just equilibrium distributions, local thermal equilibrium.
yes,
So, yeah.
I see. Thanks. This is
Thank
clear.
you.
We're at 2 o'clock, but we have one more question in the. So maybe let's take one last question from Morten.
Yeah, thanks. Thanks for the nice talk. I was wondering about the effective potential. I think you, if I understood it correctly, you used the 4D approach for this rather than this 3D EFT approach. Is there any reason for this? I mean, you already used DRAlgo in the Volgo code, right? So
Right. But we used Draugo to, parts of Draugo to compute Volgo matrix, but that is not for doing dimensional reduction. So I think there is simply no justification for taking the 3D effective potential and putting that into the equation of motion. I think you have to, basically rethink what is the appropriate equation of motion. And so far, no one has done that. So it is not necessarily better to put a two-loop effective potential there than a one-loop effective potential.
okay, thanks.
Okay. Thank you very much again, Jorinde, and thanks all for joining us. See you in a month.